Hello everyone, welcome to lecture number 3 of Geotechnical Engineering. Lecture number 3. So today, let us go into uh, let us go back to the formula of bulk unit weight. If you remember, bulk formula was what? Isn't it? So this was the formula for bulk unit weight, but this can also be modified. I did not give you the modifications, so I will show you how this formula can be modified, because you may you may be seeing this formula in different forms in the exams or in various problems. You may be seeing the different forms of this formula. So now this SE, do you remember this formula? I have told you about this formula. So if I try to substitute it here, what will it look like? If I try to substitute it here, then it will become, instead of SE, I will be writing GS into omega by 1 plus E. Then ultimately, specific gravity I can take common by 1 plus E. This. So this is another form in which you may find the formula for bulk unit weight. So either you can use this one, or you may have to use this one. I hope I am clear with it. Now let us go to the formula for submerged unit weight. How will it look like? Submerged unit weight. So submerged unit weight was what? It was saturated unit weight minus unit weight of water, isn't it? So what is the formula for saturated unit weight? Let us write it down. Then let us complete this line. Now if I try to simplify it, if I take 1 plus E common, then what do we get? GS water plus, so I am just simplifying it. So this gets cancelled. So ultimately what do you get? So this is also one form of the submerged unit weight. So please keep in mind. So what you should do is you always should write the formulas for these unit weights, okay, and try to memorize them. Now there was one relation between weight of solids and total weight. If you remember the relation, weight of solids and total weight. If you remember, you can start writing it down. Similarly, there is one relation between dry unit weight and bulk unit weight. So let us write down the formula. So you can write it like this: dry unit weight and bulk unit weight. So dry unit weight is equal to bulk unit weight by 1 plus moisture content. So if you look at it, it looks similar to the relation like this, isn't it? Means weight of solids is equal to W by 1 plus moisture content. So it goes the same way. The pattern is the same. So this is what you need to remember. You have to remember a lot of formulas. Lot of formulas are there. So now let us go to the second topic. So it was supposed to be the second topic was supposed to be liquid limit. So without going into the details, let us just discuss the definitions once again, so that you get a revision. So you can write it down. It is the water content. It is the water content at which the soil is practically in a liquid state. The soil is practically in a liquid state. Then let us go to plastic limit. So we will go into this definition with respect to the uh, experiment. We'll go to the definition. We'll write the definition according to the experiment that is done. So it is the water content at which a soil would just begin to crumble. A soil would just begin to crumble when rolled into a thread. When rolled into a thread of 3 mm dia. 3 mm dia. Then there was another, which is the shrinkage limit. But I recommend you to please go through the notes that you have already made before regarding this liquid limit, plastic limit, shrinkage limit. So shrinkage limit was the maximum water content at which a decrease in moisture content, a decrease in moisture content does not cause any decrease in the volume, does not cause any decrease in the volume. So the graph was like this, isn't it? If you remember. So this was the shrinkage limit, this was the plastic limit, and this was the liquid limit, isn't it? So shrinkage limit is this part. So if I reduce the moisture content below this, then the volume will not change. This was is the volume, right? Then the volume will not change. So I recommend that you go through the notes, and this graph also you go through. Like this one is the liquid state, then this one is the plastic state between plastic limit and liquid limit, then this one is the semi-solid state, and this one is the solid state. So once again I repeat, this is the moisture content, isn't it? So if I decrease the moisture content below the shrinkage limit, if I decrease it, if I go here or here or here, the volume does not change, the volume remains constant, isn't it? Then after you increase it beyond shrinkage limit, it becomes semi-solid. Then at one point of time it becomes plastic. It has the plastic property. Then at one point of time, when you increase the uh, moisture content further, you get the liquid state. So it is not that tough, it is simple. Now let us go to a topic called grain shape. Grain shape. So let us start. So grain shape, as you all have got the idea from the name itself, it is regarding the shape of the soil particles. If this is a soil sample, if these are the particles, a particular particle's shape, a particular particle's shape we're focusing on. So now why do we focus on the grain shape of the individual soil particles? Because you can write it down, shape of soil, actually soil particles, is important. Shape of soil is important in influencing the engineering behavior of the soil. Engineering behavior of the soil. Okay, now there is one important term that you should know, which is called as bulky grains. Bulky grains. Grains means the particles. Grains means the particles. So bulky grains are the soil grains where like all the dimensions of the soil particles are more or less the same. It means all uh, all the dimensions of the soil particles are more or less same. That means in this soil sample, the particles, each particles are having approximately the same shapes. It cannot be exactly same, but I am telling about approximately same. So they have the similar shapes. Now, if I try to see the shape of a grain, it is not exactly round, isn't it? A grain is not necessarily round. It can be a little bit deformed like this, isn't it? It can be like this. But in general, you cannot assume that a grain shape is totally round like this. Okay, so how can we check the diameter? How can we check the diameter of this? How can we check the diameter of this or of this? Because these are these are not fully spherical. Only sphericals can give accurate diameters, and you have seen that in the tables for classification of soil according to size, we classify them according to the diameters, isn't it? So you might think that we are classifying the soil according to the size means nothing but the diameter. The table that you have got in your fourth semester, I remember I have written it in the blackboard. So you may think that the classification is given in the form of diameters, but the soil particles may be like this or this. Then how can we find the diameter of these? Because soils will be mostly like this. Soil particles, they are not, you cannot expect them to be like this or this, isn't it? So then there is a term which is called as sphericity, which comes into effect. Sphericity. So sphericity is described in terms, sphericity is what? S equal to equivalent diameter by length. So a soil particle may be like this also, isn't it? So a soil particle can have length also, isn't it? So now, how can we find out this sphericity? Sphericity means how much, like, it is conforming to a round shape. Okay, how much it is conforming to a round shape. So for that we need the equivalent diameter. So the equivalent diameter, how can we find? DE, equivalent diameter, is equal to 6 VY pi to the power 1 third, where V is the volume of the particle, of the soil particle. That means we are dealing with one particular particle, right? One particle we are dealing with. So that particle, you need to find the volume. Then after the volume is found out, you will get the DE value. You'll get the DE value. Once you get find out the volume, you get the DE value. Then S, you will find out DE by L. So then you will get the sphericity. So it will tell you how much it is conforming to being a sphere. So this is a very like, this is a topic which is not rarely is rarely discussed. Okay, and generally you will see that in books also, like, this topic is not given much focus, the sphericity topic. So you can take it as an extra knowledge about the sphericity. You take it as an extra knowledge. Then according to the shapes, there are grains like flaky grains. Flaky grains, what happens in flaky grains? If this is a particles will be like this. So this dimension and this dimension are considerably higher than this dimension. isn't it? So thickness is very less. Okay, thickness is very less compared to the other two dimensions, which are this and this. So this is about the flaky grains. Then one is the needle shaped grains. So obviously needle shaped grains, it will look like this, right? Needle shaped grains. So it will have some cross section like this. So needle shaped grains where is like one dimension is particularly greater than the other two. So if it is a needle shaped grain, let me draw once more. So like this needle shaped grain, so this one dimension is particularly greater than the other two, like this one is one, this one is the other. So one dimension is particularly greater than the other two. And in flaky grains, one dimension is particularly smaller than the other two. So that is the difference between flaky grains and needle shaped grains. So after that, we go to the grain size distribution, which is all about the sieve analysis. So sieve analysis, I have already discussed it with you, okay, in the labs. So you please study sieve analysis. Then all about CUCC. I am repeating because many of you uh, might not study. Okay, so please go into the revision. Sieve analysis, CUCC. It comes just after these topics which I have discussed. Then well graded, poorly graded, uniformly graded soil. Then uh, the ranges of CUCC for being well graded and all. Then there was a numerical, and from the numerical you have made the curve. So like this. So that you please discuss and revise. Okay, then let us go to the topic called plasticity index. Plasticity index, I don't clearly remember if I have discussed this with you or not. So, but plasticity index is liquid limit minus plastic limit. So it indicates the degree of plasticity, degree of plasticity. So high value of plasticity index means highly plastic. Now for clay soil, generally for clay soil, they have clay soil, generally they have high values of liquid limit. High values of liquid limit. So plasticity index, if it is WL minus WP, if WL becomes high, then plasticity also becomes high, isn't it? So um, clay soils which are having high values of liquid limit, generally you will see that it is having high values of liquid limit. uh, but in some cases you may not find high values, but um, like in many cases you will find. Okay, so uh, if you get this kind of situation, then you can say that this is a highly plastic soil. Okay, so if sometimes if sometimes you get a clay soil which has low liquid limit, okay, or let us say low plasticity index, clay soils, if you find some clay soil, okay, with low value of plasticity index, so in that case this is called as lean clay. Okay, then coarse grain soil, that means like sandy soil, coarse grain soil, coarse grain soil, they cannot obtain plasticity. Okay, they cannot obtain plasticity. That means in this curve, the liquid limit, plastic limit, it becomes same. Okay, so what happens is that IP WL minus WP, it becomes 0. So we can say no plasticity. Okay, so coarse grain soils, obviously you can relate, isn't it? If you take a sandy soil or coarse grain soil, will you find any plasticity? You will not find any plasticity, right? So this is the mathematics behind that, why you don't find plasticity, because in coarse grain soil the liquid limit and plastic limit are same, and when they are same the IP value becomes 0, and ultimately there is no plasticity in the coarse grain soil. And the last topic for today's video is the we'll classify the soils based on plasticity index. So if plasticity index is 0, obviously it is non-plastic, then less than 7, low plastic, then if it is 7 to 17, then it is medium plastic, greater than 17, highly plastic. Okay, so you have to please remember these. So in the next video I will move forward with topics called consistency index, then IL liquidity index, and I think I will make a short video on it. Okay, short video like uh, on these two topics. It will be lecture 3.1. Okay, so thank you very much for listening with attention. Thank you very much.